Hello, this is the section 11.2 lesson. In this section we're going to get a hypothesis test that at first glance looks very different than anything we've done before, but it has a lot of interesting applications, and the basic process for setting it up and doing it aren't going to be a whole lot different than what we've seen before. For this lesson you're going to need a print table A4 from page 755, and you'll also need your calculator. So in our first example, the author of the textbook drilled a hole in a die and filled it with a lead weight and then proceeded to roll it 180 times. The results are given in the frequency distribution. So this distribution on the right says, for instance, we got a 1 24 times, a 2 28 times, etc. The question we want to try to answer here is, does the loaded die appear to differ significantly from a fair die that has not been quote-unquote loaded? Well, before we try to answer that question, we need to define a term and then make a couple of observations. When we roll a die like this, we have an example of what's called a multinomial experiment. Now, back in chapter 4 when we talked about binomial distributions, we talked about a binomial experiment. A binomial experiment, we had two outcomes, success or failure. A multinomial experiment, going to have more than two outcomes. So this definition here is very similar to a binomial experiment. The biggest difference is number 3. All outcomes of each trial must be classified into one of several different categories. Here I have 6 different possible outcomes, either 1, 2, 3, 4, 5, or 6. And so we have an example of a multinomial experiment. This type of test we're going to talk about can be applied to these types of multinomial experiments such as this. Okay, so now let's make an observation here. Here's our frequency distribution, outcomes 1 through 6, our observed frequencies, 180 times total. Now, if the die were not loaded, then we would expect to get a 1 1/6 of the time, a 2 1/6 of the time, etc. 1/6 of 180 is 30. So if the die were not loaded, we would expect to get a 1 30 times, a 2 30 times, etc. Well, if we compare those observed frequencies to the expected frequencies, we note that there's not a lot of difference. Those numbers obviously aren't identical. Some of the observed frequencies are a little less than 30, some are greater than 30, but there isn't a whole lot of difference. So the observed frequencies are not significantly different from expected frequencies. Now I put significantly in quotation marks because we haven't defined what exactly we mean by significantly. But just glancing at them, there doesn't appear to be a whole lot of difference. Now, some people may argue with that conclusion, but we're going to quantify it here in a little bit. So what this means is that our loaded die does not appear to be that much different from a fair die. So adding that lead weight didn't change a whole lot. Well, what we want to do is quantify the difference between the observed and the expected frequencies and test if it's significant. In other words, we want to define what we mean by significantly different. So before we start doing the calculations, we need to refresh our memory on definition of one term, a distribution. Distribution describes the probabilities or frequencies of a procedure. Remember, a procedure is some activity that where we don't know the outcome until we actually do it. A distribution can be given in the form of a table, a graph, or a formula. And we've seen all 3 of these different forms back in chapters 5 and 6. Well, what we have in this case are really 2 distributions given in the form of tables. We have the frequency distribution of the loaded die and then the frequency distribution of a fair die. And we are comparing those 2 distributions. Our claim is that those 2 distributions really aren't that much different. Okay? So one way we may state that claim is that the distribution of the loaded die quote-unquote fits the distribution of a fair die. And by fit, we mean that there isn't a lot of difference between those 2 distributions. So the type of test that we're going to do here is what's called a goodness of fit test, or some books might call it a chi-squared goodness of fit test. We are testing if those 2 distributions are different or not. Another way we might state the claim is that the sides of the loaded die occur with equal frequency, because in the fair die they do occur with equal frequency, and we're claiming that there isn't that much difference between those 2 distributions. So the sides of our loaded die occur with equal frequency is another way of stating our claim. Well, we need to define some notation here before we start setting up our hypotheses. Let's let P1 equal the proportion of 1s when rolling the loaded die. P2 would be the proportion of 2s when rolling the loaded die. P3 would be the proportion of 3s, etc. Now this is a little different than what we saw in the last section. P1 here is not a proportion from one population. It's just the proportion of 1s. P2 is a proportion of 2s, etc. Okay. So again, our claim is that the two distributions fit each other. Well, our claim in mathematical notation is going to be the same as our null hypothesis. It's the claim that P1 equals P2 equals ... P6 equals 1/6. Claim is that all of those proportions are equal and they all equal the number 1/6. Again, we're saying that those outcomes occur with equal frequency, 1 divided by 6, because we have 6 different outcomes. So in this type of claim, our claim and our null hypothesis are always the same. Now our alternative hypothesis really isn't important, but we'll just state it for completion. It's the statement that at least one of the proportions is not as claimed. So the opposite of them all being equal to 1/6 means that at least one of them does not equal 1/6. Alright, so next we need to calculate our test statistic, and this is one that we're going to do by hand. We're going to do it by hand because not all of our calculators will do it automatically for us, and also the formula isn't terribly complicated. So in our test statistic we need a measure of the total difference between the observed frequencies and the expected frequencies. And that total difference is what we call the total deviation. Okay. And here's our formula. The test statistic is a chi-squared value. It's not a z-score, it's not a t-score, it comes from a completely different type of distribution, chi-squared. And it's calculated by taking each observed value minus the expected value, corresponding expected value, square it, divide it by the corresponding expected value, and then we add it up. It looks kind of complicated, but if we organize things, it's not too bad. Now let's talk real quickly about this chi-squared distribution. There on the left we see a graph of the chi-squared density curve. Notice it looks kind of like a bell curve, but it's not symmetric. Meaning if we draw a straight vertical line through the high point of the graph, the left half is not a mirror image of the right half. Second difference, the values are non-negative. All chi-squared values must be positive. And then third difference is that the distribution is different for each number degrees of freedom. Degrees of freedom, here we'll talk a little bit more about what that means. So there's our chi-squared distribution. Okay. Now to calculate our test statistic, we are going to form a table like this. And on the left I have our outcomes. Beside that we have our observed frequencies, which come from the given data. And then right beside that we have our expected frequencies, which are all 30 in this case. In our next column we're going to take each observed value minus the corresponding expected value. So the first one is 24 minus 30, 28 minus 30. Notice some of those are negative and some are positive. In the next column we're going to square each one of those differences. So negative 6 squared is 36, negative 2 squared is positive 4, etc. Now notice that all of those numbers are positives because whenever we square a number it's always positive. Next column we're going to take each one of those squared numbers and divide it by the corresponding expected frequency. So for the first one we take 36 divided by 30 to get 1.2. Next we take 4 divided by 30 to get 0.133, so on and so forth. And then our last step, we add up those numbers in the right hand column to get our chi-squared value, which in this case is 6.8. Now if we want to calculate our p-value, this types of tests are always right-tailed. So the p-value is going to be the area to the right of 6.8 underneath chi-squared curve. But we don't have a table to find areas, and not all calculators can calculate the p-value, so we're going to use a different method here. Okay, so we calculated our chi-squared test statistic, and we pointed out that our calculators can't find p-value and we don't have a table for the p-value. So we're going to use a different method for coming to our technical conclusion. It's what the book calls the traditional method. Now, if you've been reading in the book, you'll see that the book talks about 3 ways of doing hypothesis tests. They have the p-value method, which is what we've been doing. They have the traditional method, which is what we're going to talk about here in a minute. And then the third way is what they call a confidence interval method, where they calculate confidence intervals and then use those. They're all different ways of coming to the same technical conclusion. In the traditional method, we compare our chi-squared test statistic to a critical value. We're going to get this critical value from this table A4. If the chi-squared value is greater than the critical value, then we reject the null hypothesis. If it's less than the critical value, then we do not reject the null hypothesis. Okay? And again, our critical value comes from this table A4. Now here's table A4, titled chi-squared distribution. Along the top we have the area to the right of the critical value. Now that area is going to be our significance level alpha. Along the left we have degrees of freedom. Our degrees of freedom is the number of categories minus 1. Now in this problem no significance level was given, so we'll use 0.05 corresponding to a 95% confidence level. Our number of categories is 6, because we have 6 different possible outcomes, so our degrees of freedom is 5. So we go to that row and that column to get our critical value of 11.071. So that's our critical value, 11.071. Okay. Now our chi-squared value is 6.8, which is definitely less than the critical value, and so we do not reject the null hypothesis. Now this looks kind of the opposite of the p-value method. If we have a small p-value, then we reject the null hypothesis. In this case we have a small test statistic, so we do not reject the null hypothesis. Again, it seems kind of opposite, but in a minute we'll talk about how the p-value method is related to this traditional method. Okay. So now we word the final conclusion the same way. Does the original claim contain the condition of equality? And the answer is yes. Our null and our original claim are always the same. It's always that our proportions equal something. So do you reject it? No, we do not. So there is not sufficient evidence to warrant rejection of the claim that the distribution of the loaded die fits the distribution of the fair die. So we are not rejecting the claim that there isn't a lot of difference. So what this means in even less technical terms is that the loaded die does not appear to be significantly different from a fair die. They may not be identical, at least according to our sample data, but that difference is not significant enough. Now, requirements for this test: first, the data have been randomly selected. Again, that's always a requirement. And then second, the sample data consist of frequency counts for each of the different categories. So our data have to be frequencies. They can't be measurements or weights or anything like that. And then number 3, for each category the expected frequency is at least 5. So that means we've got to have a fairly large sample size in order for this test to be applied. Now in our second example, in 1996 the manufacturer of M&Ms reported that the distribution of the colors of plain M&Ms was 30% were brown, 20% were yellow, 20% were red, etc. And so a few semesters ago in my class we tested if this distribution really still applied to current M&Ms. So we tested the claim that the current distribution of M&Ms fits the 96 distribution. What we mean by that is that the current distribution isn't significantly different from the 96 distribution. Stated another way, we're claiming that today 30% are brown, 20% are yellow, 20% are red, etc. So that's our claim. So set up our hypotheses. We're claiming that the proportion of brown M&Ms is still 0.3, the proportion of yellow M&Ms is still 0.2, etc. That's our claim, which is the same as the null hypothesis. The alternative really isn't terribly important, but it's the statement that at least one proportion is different than claimed. Okay. So in class we counted 1,191 M&Ms. We got that 154 of them were brown, 201 were yellow. etc. So there's our observed frequencies. So now to calculate our test statistic, we set up our same table here. Notice again we've got 6 different categories, so we have a multinomial experiment. Each M&M is either brown or yellow or red, etc. Here we have our observed frequencies. Now, our expected frequencies are not all going to be the same. To calculate our expected frequencies, we're going to take the sum of the observed frequencies times the claimed proportions. So I've got the claimed proportions there in parentheses beside the color. So we take 0.3 times 154 to get 357. And then 0.2 times 201. No, excuse me. We take 0.3 times 1191 to get 357. And then we take 0.2 times 1191 to get 237, etc. Now, I've rounded those expected frequencies off to whole numbers, but that doesn't have to be the case. You can leave those in decimal form. But notice that not all of those expected frequencies are the same. Some are the same, but some are different than the others. So there we have our observed and our expected frequencies. Now we calculate the same as before. Take observed minus expected, square it. Notice that those numbers get quite large. Next we take those squared numbers divided by the corresponding expected values, and then we add them up. So we have a very, very large chi-squared value, 439. Now our critical value is the same as before. Because we still have 6 categories, so we have 5 degrees of freedom, we'll use significance level of 0.05. So our critical value is 11.071. We have a our test statistic is much, much larger than the critical value, so we would reject the null hypothesis. Word it in the same way. The original claim does contain equality. Do you reject it? Yes, we do. So there is sufficient evidence to warrant rejection of the claim that the current distribution of M&Ms fits the 96 distribution. What that means in even less technical terms is that it appears the distribution has changed. Now exactly what the current distribution is, I don't know, but it's not the same as the 96 distribution. Now let's quickly compare this traditional value or traditional method to the p-value method. What we're doing in this type of claim is comparing the observed values to the corresponding expected values. If they're close to each other, as they were in the first example, then we have a small chi-squared value. And that means we have a large p-value. Small chi-squared value means that the area to the right is very large. And so we would not reject the null hypothesis. And we would conclude that there is a good fit, or that the two distributions do indeed fit each other. So a small chi-squared value means we have a large p-value. In both cases, we do not reject the null hypothesis. If the observed and expected values are far apart, as they were in the second example, then we have a large chi-squared value, which means that the area to the right is very small, so we have a small p-value. And in both cases, we would reject the null hypothesis, and we would conclude that the two distributions do not fit each other. Now real quickly, let's talk about how we could do this on our calculator. Now, not all calculators can do this type of test. Some of the newer calculators, the TI-84 pluses, can do it. Some of the older calculators, the 83s, cannot do it. So your calculator may or not have this command. But in order to do this, we first need to enter our observed values in list L1 and the expected values in list L2. And so remember, the command for entering data into list is you go stat, edit, edit. You clear out any data that's already in those lists, and then you enter the data. So here in L1 you see the observed values from our M&M data. Right next to that you have the expected values. Now you have to manually calculate the expected values. Remember, you do that by taking the claimed proportion times the sum of the observed values. And so you enter that in list L2. And then the command is stat test option D chi-squared goodness of fit test. Now again, not every calculator is going to have this command. So there you see it on the left, chi-squared goodness of fit test. In the middle window you see how we enter the information. You enter next to observed, you enter the list that contains the observed values, and then right below that you enter the list that contains the expected values, L1 and L2 in this case, and then DF is degrees of freedom, which again is the number of categories minus 1. And then below that you select either calculate or draw, and then to the right you see the window for the results. Chi-squared goodness of fit test, you have your chi-squared value. Now that chi-squared value may be different than the one that you get by hand, and that's because when you do things by hand we round in every step, and when the calculator does it, is not round until the end. So its value may be a little bit different. Right below that you have the p-value. Notice in this case it's 5.7 times 10 to the negative 93. That means we have 0.0, now you have 92 zeros and then 5.7. In other words, it's an extremely small p-value. It's practically 0. Below that we have df, which is degrees of freedom. Right below that we have contribution, and this is a list of numbers that is essentially the numbers in the right hand column of our table that we use to calculate the chi-squared value by hand. For our purposes this isn't terribly important, but for other people it may be more important. But from this you can use either the chi-squared value and then use the traditional method, or you can just use the p-value. Either way should give you the same technical conclusion. You either reject the null hypothesis or not reject it. So that's it for this lesson. The homework is titled Section 11.2.